Welcome to this introduction to algorithms. In this video, we'll explore what algorithms are and the different types of algorithms used in computer science and problem solving. But first, what exactly is an algorithm? An algorithm is a step-by-step procedure for solving a problem or accomplishing a task. Think of it as a recipe or a set of instructions that, when followed correctly, will always produce the same result. Let's look at a simple, real-world algorithm example, making a sandwich. First, you take 2 slices of bread. Second, spread peanut butter on one slice. Third, spread jelly on the other slice. Finally, put the slices together. This simple set of instructions is an algorithm. It has a clear input, the ingredients, a defined process, the steps, and a predictable output, a sandwich. All effective algorithms share certain characteristics. First, they have well-defined inputs and outputs. Second, they are clearly defined with unambiguous steps. Third, they are finite, meaning they eventually terminate. Fourth, they are effective, solving the problem correctly. And finally, they are feasible, meaning they can be executed with available resources. Now, let's explore the main types of algorithms used in computer science and problem solving. There are several major categories based on their approach to solving problems. First, let's look at search algorithms. These algorithms are designed to find an item with specified properties within a collection of items. Common examples include linear search, where we check each item one by one, and binary search, which efficiently finds items in a sorted list by repeatedly dividing the search space in half. Next, we have sorting algorithms. These algorithms arrange data in a particular order, typically ascending or descending. Common sorting algorithms include bubble sort, which repeatedly steps through the list and compares adjacent elements; merge sort, which divides the input array into 2 halves, sorts them separately, and then merges them; and quicksort, which selects a pivot element and partitions the array around it. Recursive algorithms are particularly elegant. These algorithms solve problems by breaking them down into smaller, similar subproblems, and then calling themselves to solve these subproblems. A classic example is calculating the factorial of a number. To find factorial of n, denoted as n exclamation mark, we multiply n by the factorial of n minus 1. This continues until we reach our base case, factorial of 1 equals 1. Dynamic programming is a powerful technique. It solves complex problems by breaking them down into simpler subproblems and storing the results of these subproblems to avoid redundant calculations. A classic example is the Fibonacci sequence. Instead of recalculating values multiple times in a recursive approach, dynamic programming calculates each Fibonacci number once and stores it for future use. Greedy algorithms make locally optimal choices at each step. These algorithms always select what currently looks like the best option, hoping that these local optimums will lead to a global optimum. A classic example is the coin change problem when using a system like US currency. To make change with the minimum number of coins, we can greedily select the largest coin denomination that's less than or equal to the remaining amount at each step.